Hi, my name is Shahnawaz. In this lecture, we are going to introduce the projective modules. But before that, we are going to prove that any R module can be expressed as a quotient of a free module. Now, let us prove this proposition. So any R module can be expressed as a quotient of a free module. Now suppose if we have any, say, R module M, then what we have to prove? We have to prove this M, this is actually isomorphic to some quotient of a free module. Suppose if F is over free module, then this M is isomorphic to some quotient group of F. So let us suppose this is G here, where G is submodule of F. So this is what we have to prove, that any module R module M is actually the quotient of a free module. Now let us prove this. Let F be the direct sum of, say, so let F be the direct sum of size of M copies of R. That is, this F is actually direct sum of copies of R, where this direct sum runs over the elements of M. This means that there are as many as summands in this direct sum as the number of elements in M. So now if this is free, so obviously it's a free module, being the direct sum of copies of R. So now F being a free R module, so it must have a basis. So F is a free module. Now let us define it as basis. So let say B, which contains the elements of the form xm, where M is in M, be a basis of F. So one can note here, each element in M can be identified as a basis element of this free module F. So this means that the rank of F is actually, so rank of F is actually the size of M, because basis of F contains as many elements as the number of elements in M. So this is our basis. Now we can define a function. So define a map, say gamma, from this basis to M as, so this gamma takes an element, a basis element, say xm, and it maps this basis element to m. So actually this xm, this is a vector, and it has as many components as the number of elements in m. So this is our basis, and this is our module m, and this is our function gamma. So obviously we can embed this basis into f. So this is the inclusion map. So one can invoke the universal property of modules here. So we can extend this gamma to a unique or linear map from f to m. So therefore, by universal property of free modules, and this universal property, this is what we have done in the previous lecture. So there exists a unique or linear map, say phi from f to m, given as so this phi and gamma, they must agree on the basis of f. So we can define this phi as, so this phi of xm is same as gamma of xm, because they have to agree on the basis of f, which is actually m, for all m in m. So this is how this phi is defined. So this gamma, it takes element xm and it maps it to this little m, and this is our phi. So this takes xm here and it maps this to gamma of xm. So one can note here this phi is surjection. So obviously phi is surjection, because each element in M is identified as a base element of F. So for each M here we have an element xm here. So one can invoke first isomorphism theorem on modules. So invoking first isomorphism theorem on modules. We have now this P being a surjection, so this M, this must be isomorphic to some quotient group of F. We have M is isomorphic to F mod it is kernel. So since kernel of phi is submodule of M of F, so this proves that M is, this shows that M is the quotient of a free module. Now let us move to projective modules. Now we have studied earlier that if A and B, and suppose they are R modules, and if we look at this set, this is the set of R linear maps, all R linear maps from A and to B. So this has an R module structure. So what we did earlier, so if we have say an R linear map between these R modules, so this phi, this induces a module homomorphism. So if D is any other R module, so this phi induces an R module homomorphism between these sets, home of dA to home of dB. Note that these are R linear maps. So this phi induces this phi star. Now this phi star is defined as, so phi star when operated on an element of this set, which is a linear map from D to A, so it takes this F to phi star F, which is actually phi composite with F. It is like this. So this is our module D, this is A, this is B, this is phi. Now we have to define phi star from this set to this set. Now let us take an element of this set. So that will be a linear map between D and A, from D to A. So let us take that map to be F. So this phi star carries out this map, this is phi star, to this map here. So it takes an element of this set to this set. Now an element of this set is actually a linear map from D to B, I mean from this module D to B. So this is our phi star F. So one can note here this phi F, phi composite with F, is actually a map from D to B. So this can be defined as phi composite with F. We also did a theorem in earlier lectures that given any exact sequence, say of R modules A, B, C and 0, this is our short exact sequence of R modules, then for any D module, for any R module D, so if R is our and D is our R module, then this exact sequence induces this sequence here. So 0 goes to home DA to home. So if this is phi, this is psi, so this is our phi star then, and this is home DB, this is home DC, so this is psi star. So one can note here 0 goes in and 0 comes out. So here 0 goes in but 0 does not come out. So that means here psi is surjective does not imply psi star is surjective, but phi being injective implies phi star is injective. And we did an example in the previous lectures to verify our claim that this psi star need not be surjective. So if we look at this exact sequence, 0 goes to, so in place of A we take 2z, B as z and C as z mod 2z. So then indeed this is an exact sequence. So this is 2z, this is z, this is z mod 2z, and this goes to 0. So this is the inclusion map here, and this is the canonical map here. So if we take if we take d to be equal to say z, say z mod 2z, then this exact sequence induces this exact sequence 2z. So if we take this sequence here, so this is z mod 2z comma 2z, this goes to z mod 2z comma z, this goes to z mod 2z, z mod 2z. So 0 does not come out here, because if we this is home and home. So if we look at this set, it consists of two elements. One is the 0 homomorphism and other is the identity homomorphism. But when we look at this set, this contains just 0 homomorphism. So this one and this identity homomorphism does not have a pre-image. So this psi star here is not surjective. Now those modules, I mean, if D is a module such that this psi star is surjective, then D is called a projective module. Now let us make this as a remark. So given any R module or modules A and B and a linear map phi from A to B. So if D is an R linear an R module, then this phi induces a linear map, this induces a linear map P star from home DA to home DB. So note that surjectivity of this phi does not imply surjectivity of phi star. So take this example, take A to be equal to Z, B to be equal to Z mod 2Z, and this D to be equal to Z mod 2Z, then phi from Z to Z mod 2Z is surjective, but phi star from home Z mod 2Z Z to home Z mod 2Z Z mod 2Z is not surjective, as this set consists of only 0 homomorphism. So certain types of modules, certain, this is remark 2, certain types of modules P have the property that for any surjection let us rename this module as P. This is module P here. So certain types of modules P have the property that the above map phi star from home PA to home PB is surjective. Such modules P are called projective. Such modules are called projective modules. Now let us define these projective modules. There is an alternative definition, and this is a consequence of some result which we are going to prove in the upcoming lectures. So let us define these projective modules formally. So an R module P is called projective if it is direct summand of a free R module. That is, if this is a free module F and another module Q, such that F is a direct sum of P and Q. So if this P is a direct summand of this free module F, then P is called projective.